right, so this is question 7 on your practice test for Unit 5. So we have 30 kilojoules of heat is added to 0.3 kilograms of CO2 in a rigid tank initially at 30 degrees. We want to find the entropy change of the gas in kilojoules per kilogram. So let's go ahead and write down what we know. And sometimes a picture is good. I don't know if it's any help here, but here's my mass of CO2. Okay, so I've got a mass of 0.3 kilograms. I'm going to add some heat. It's color coordinated a little bit. Ba-dum. Here's our Q going in, 30 kilojoules. Perfect. And it's a positive 30 because it's going into the system. And then it's initially, let's go ahead and get that. So it's initially T1 is, goodness, T1 was 30 degrees. Okay, 30 degrees. And we want to find the entropy change for the process. All right, entropy change for the process. So, oops, not sigma, entropy change. So that's a delta. Delta S, and we want it in kilojoules per Kelvin. So that's actually delta capital S, I believe. Yeah, okay. So, yeah, there's some assumptions on here. And there is one little piece of critical information that was missing from this problem statement. So number one, we're going to assume it's an ideal gas. I won't worry about proving that we've got an ideal gas or anything like that, but yeah, we'll say we're going to assume that we've got an ideal gas. And the other piece of information that should have been told to you is to assume that the specific heats are constant. Okay, you don't necessarily need to. There are tables that you can use, but we've never used them in class before, so let's not start now. Um, so yeah, do need a CV value. So this is information again that would be given to you. So we're going to use 0.7. 0.7 joules per kilogram K. Okay. Alrighty. So again, this highlighted stuff was not originally on there, but you should be given that information to, yeah. All right, so to figure out how we are going to get our change in entropy. All right, so this is delta big S, which is M delta little s. We have the mass, right? That's our 0.3 kilograms. And then we do have an equation that we can use. There we go. So we have relationships for ideal gases, and we are assuming specific heats are constant. And then the other thing that we're going to do is we're going to use one of these guys right here. So the information that we've got says it's a rigid tank, right? Yeah, rigid tank. So let's use this one. This one's probably going to be much more convenient for us. I'm going to write this down here. And that's actually something I should probably put in my assumptions. It's a rigid tank. Volume is assumed to be the same. So is the specific volume. All right. And I've got a delta little s for an ideal gas with constant specific heats. And we're going to use the one with CV. CV, natural log T2 over T1 plus R, natural log V2 over V1. This R is the specific gas constant, and I could calculate that based on my universal gas constant, R bar, over my molar mass. But turns out I really don't need to. And the reason is because if my specific volume is the same, the natural log of 1, V2 over V1, if that's the same, that ratio is 1, natural log of 1 is going to be 0. So it doesn't really matter, right? You do need to make sure that those temperatures are in absolute temperature units. So let's make sure to do that. So we have 273 plus 30, which would be 303 Kelvin. And so that's great. Great. So 0.3 kilograms times CV, 0.7 joules per kilogram K. Natural log of T2, oh, don't know T2, but we'll get them in a second, over 303 Kelvin. Okay, and so of course we are definitely going to need to know what that T2 is. Okay, so gotta find T2. And we're going to do that by applying our first law. Our first law or our energy balance for a closed system. So our closed system, first law energy balance is Q minus W equals delta U plus delta kinetic energy plus delta potential energy. And those are two more assumptions that I'll make. Delta kinetic energy, delta potential energy, both are equal to 0. Bump it up. I do know how much heat is being added. I also, so that's good. And then I'm going to say that my work is equal to 0. And the reason being is because I have a rigid tank. So there's no expansion or compression, no boundary work, and there's no like weird paddle wheel or anything like that in there. So all I've got is Q. So I've got Q is equal to mass times delta little u. And because I've got an ideal gas with constant specific heats, this is going to be mass times CV delta T, right? So mass times CV times T2 minus T1. And so I could just solve for T2 because that's what I'm looking for. So it's going to be Q over mass times CV plus T1, right? So I've got a temperature of 445.86 Kelvin. Perfect. So I need that. So 445.86 Kelvin. Again, has to be in absolute temperature units. And so we've got a 0.08 kilojoules per Kelvin. And so if anybody asks you, is this possible or not, you would say, yes, of course it's possible because well, actually, no, we can't really say anything about this being possible or not. I should back up. So I'll actually write that then. Can't say if it's possible or not because and we need to know sigma, right? Sigma would have to be greater than or equal to 0 for that process to be possible. And we actually don't have that because we would need to apply an entropy balance. And if you think about the terms that are in that entropy balance, you would need to have the temperature at the boundary at which heat transfer takes place. We don't actually have that information, but yeah, so okay. But other than that, I think we're good. Yeah, I think we're good. All right. So yeah, we'll leave it there. And if you have questions, let me know. Thank you.